Bismillah ar-Rahman ar-Rahim. This is the third online lecture for the mass balance for a CSTR. Let's consider this example or this exercise. The lake has a volume of 40,000 meter cube. The average depth of the lake is 1.7 meter. Okay. Receives an input of a pollutant from three sources. So there is three sources of pollutant that coming to the lake. So this is the lake. And there is three sources of pollution. There is a factory, the charge, there is a point source. There is an atmospheric deposition, and that is an endpoint source. And there is also an inflow toward the lake. Okay. The first question is to find K. Assuming that A is equal 18,500 meter cubic per day. So let's look at it. Now you could see here there is no settling. So if he did not mention that there's no settling, so you don't have to include settling. So A, the equation of A, which is the assimilation factor, is equal to Q plus KV. This is this. Let's just see this question number one. You know that A is equal 18,500, and put that units, meter cubic per day, is equal to the Q, and for the Q is 7,600 meter cubic per day, and that is the Q. Plus K. K is unknown. He wants to find K. So K is unknown times the volume. The volume, you could find it from here. The volume is 40,000 meter cube. This is the volume. Which means if you look at the units, K has to be 1 per day. So when you plug in into your calculator, you will find K is equal to 0.27, let's say 2 per day. That is the first problem. Number two, what is the steady state concentration in the lake? So you want to find out the steady state concentration. This is the solution for number two. C is equal the loading over A, the assimilation factor. What's the loading? Now you're going to put all the loading. The first loading. This is the concentration of the factory. This is the first loading, the point source. So 40, we will have it in grams. 40, you change kilogram to gram, that's 40,000 gram, and that is per day. That's the first loading. Loading number two is the atmospheric deposition, the non-point source. Now, the non-point source, we have to account for the flux. Now, the flux is given, the deposition is given 0.7, this is plus 0.7 gram per meter square per day. That's times. Now, you can see that it's gram per day, so you have to get rid of the meter square, which is the surface area of the lake. Now, how are you going to find the surface area of the lake? You know that the surface area is equal to the volume divided by the average depth. What's the volume? 40,000 meter cube. That is the volume. And what is the average depth? 1.7 meter. So the area, let's say the surface area, is equal to 40,000 over 1.7, and that is 23,529 meters square. Now we're going to put this here, 23,000 529 meters square. You can see meters square, that's going to be gram per day. Now, do we have another loading? Yes, we do. We have this, the inflow, 76,000 per day, meter cube per day, and we have the concentration of that inflow. So plus 7,600 meter cubic per day times. Now we want to make it gram per day. So we want to change this. You want to change this liter to meter cube, and you want to change this milligram to gram. So let's put it here. 10 milligram per liter. Liter to meter cube. 1 meter cube is equal 1,000, and 1 milligram to gram. 1 gram is 1,000 milligrams. So 1,000 with 1,000, and milligram with milligram. Okay, so 10 milligram per liter is equivalent to 10 gram per meter cube. This is times 10 gram per meter cube. Now we have the cancellation of meter cube with meter cube. That's gram per day. So now we are fine in terms of units. Divided by A. A is given 18,500. So now we will sum up all these loading and divide it by the A, the assimilation factor. So the concentration C, the steady state concentration, is equal to 7.16. 7.16 gram per meter cube, because since everything is, it is gram per day, yeah, gram per meter cube, which is equivalent to 7.16 milligram per liter. Let's look at the second one. What is the mass rate in mass per time for each term in the mass balance? Okay, so now we have to account for each one of them. Let's look at the mass rate for the loading. You have to sum up all the loading here. This one, and all of this. Okay? Or we have to make inflow plus the loading of the atmospheric deposition and the factor discharge. Let's look at problem number 3, mass rates. Loading. You just sum them all up. That's 132,470 gram per day. Sum up of all the loading. This is the sum of all loading. All loading. How about the outflow? The outflow is by multiplying the flow rate, which is the same as the inflow flow rate, times the concentration. And that is, you can see that the flow rate, 7,600 meter cubic per day times 7.16. Now we're going to make it as gram per meter cube, which is the same as milligram per liter. Meter cube with meter cube, that's going to be gram per day. If you multiply this by this is going to give you 54,416 gram per day. And then you'll have the reaction rate, and that is rate K, V times C, and this is first order. Now, K was, we found the K initially, 0.272 per day, and we have the volume. Let's see, where did we have the volume? The volume is given 40,000 meter cube, and we have the concentration, which is 7.16 gram per meter cube. You can see here meter cube with meter cube, that's gram per day. Good. So the reaction rate which is going to be subtraction from it 78,044 gram per day. Now you could go ahead and check if that's going to be equal to W. So you can see that if W is equal to QC plus KVC, when you add up this to this, you'll end up with the loading 132,470. And that is just only a check of whatever we just did, all this. Okay, let's look at and this the characteristics of the system. What is the residence time that represents the average time of a particle of interest remains in the system. This is, if you're talking of an organic particle, and this organic particle is inside the reactor, how long it will take in terms of time inside the system, inside the CSTR. Let's look for the general equation. The time it will take the particle to stay in the system. General equation. This is how much X, how much of the organic we have, over dx over dt, which is how fast it is removed. How fast X is removed. How much is it in the system, and this is how fast it is removed in the system. Now, in terms of water, movement of water with the organic coming into the CSTR, and water and the organics as a particle moving outside the CSTR. In terms of water hydraulics, the water hydraulic residence time, this is for the water, it's simply volume over Q, simply. Now, in terms of pollutant residence time, in terms of water, it's volume over Q. In terms of pollutant, let's say TC, that's equal to volume times concentration divided by QC plus KVC plus, if there is a settling velocity, times A times C. Now there's a lot of C's here. Let's cancel out all the C's. So if you cancel out all the C's, so then the pollutant residence time, I'm going to put it here, it will be equal to the volume over Q plus key volumes plus velocity times the area. Of course, this is the surface area of the lake. Okay, now let's give you another example. For the lake we considered earlier, what are the hydraulic time or the hydraulic residence time? What is the pollutant residence time? Okay, let's put the hydraulic residence time, T, for the water hydraulics, it's volume over Q, and you know the volume is equal to 40,000. It was given in the example, and the Q was also given 7,600 meter cubic per day, and this would give you 5.26. So this is how much the water will stay inside the CSTR. 5 days and 0.26 of the day. How much the pollutant will stay in the CSTR? Let's look and put the equation. Now here there's no settling. Remember, there's no settling, so you have to divide volume by Q plus KV. That's it. So volume over Q plus K volume. Now what is the volume given? 40,000. Q is 7,600 meter cubic per day plus K, we found it to be equal 0.272 per day times the volume, which is 40,000. And this would give you 2.16 days. Okay, so the organic will stay inside the CSTR 2 days and 0.16 of the day. The water will stay inside the CSTR 5 days and 0.26 of a day. So now, we mentioned before that the loading as a function of time divided by the volume, remember this is the loading as a function of time, is equal change of concentration with time plus C Q over volume plus K plus settling velocity over the average depth of the CSTR. So remember, I'm trying to only to review the general solution for the problem that we have. Now, when we have that the loading is equal to 0, the whole thing will change to what? Remember, this is lambda. The whole thing will change to CT is equal initial concentration of the pollutant e to the power minus lambda t. And we mentioned lambda describe the system response to loading. Okay? Of course, we could compare systems based on suitable procedures, and there is no need to change lambda to A, because A and lambda are different. Okay, so lambda is very important, especially when we are discussing CSTR system, that is the response of that system to loading. Okay, let's look at this example. Or before we just go to the example, let's just define response time. It is the time that it takes for a CSTR to complete a specific percentage of its recovery from a loading event. Okay, so the time it will take the system, the CSTR, to complete a specific percentage. Are you talking about 99% removal? Okay. Are you talking about response to clean up 50% of removal? So this is the meaning of response time. Let's look at general, well, before we do that, let's just give an example. We're going to use the same example we had before. And we want to calculate the eigenvalue, and the general solution assume the load terminated at time 0, which means that the loading is equal to 0. Okay, now remember that example that we had before, that C naught is equal 7.16 milligram per liter. And lambda, since if someone asks you what is the eigenvalue of that, so lambda is equal to Q over volume plus K. And that is, of course, there is no settling here because he did not specify settling in the example. 7,600 meter cubic per day divided by 40,000 plus K, which is 0.272 per day, and that is the units are homogeneous here, meter cube cancelled meter cubed. It's going to be per day at the other side, and that would give you the eigenvalue is 0.463 per day. And we can compare now how important different processes are by comparing lambda from this process to lambda to the other process. Okay, so this will also determine, and we're going to use that for the response time. Let's say if we are looking for 50% removal, for 50% removal, and that is the response time, which means we can use the equation that CT is equal C naught E minus lambda T. CT is 50%, so it's 0.5 C naught equal C naught E minus lambda. So lambda is equal, let's just leave lambda for now, lambda, and let's just call T and then C naught with C naught, you will end up with the equation that's ln 0.5 equal minus lambda t, and this is t mean 50%, so t 50%, it's going to give you ln 0.5 over minus lambda and 10 point ln 0.5, and that is 0.693, and that's going to be minus, so lambda going to be positive here. So now we could put it like lambda as given here, 0.693 over 0.463 per day, and that will give you, I need to find this now, so calculator, 0.693 over 0.463, and that will give you 1.50 days. So it will take 50% of the removal of that waste in 1 day and a half. Okay. So the general response time equation, I'm gonna put it here, that T50, 50 of course percent, is equal 0.693 over lambda, and that's what we just found here. And if you want to put it as a general equation, T as any time is equal 1 over lambda times ln 100 minus 100 minus x. This is x, it is the days. I mean, x is the percentage, sorry. So Tx will give you in days, but x here is the percentage, 50%, 60%, 75%, 90%, 95%. And that is, so x, very important, is equal percentage recovery. Okay, so let's look for the formula, T50. T50, we just found it, 0.693 over lambda. This is from Steve Chopra. You could look at it, table 3.1. T63.2, it's 1 over lambda. You could just do the same process. And T75, it is 1.39 over lambda. You could use this equation and plug it in. T90% of the removal, it's 2.3 over lambda. And T95% of the removal of the organic, 3 over lambda. And this one is 4.6, T99% removal, which is really good, over lambda. And that's it. But just look at the values of, this is the last slide, that this is the response time. Fraction removal, 50% removal, 60% removal, 70% removal, 100% removal. And you can see this is the time of the days that it might take to remove the following organic pollutants with the K values. Now, look at the K values, 0.0027, and look at 2.72. Look how much is the time. So to remove 50% is such a small time. But when you go even to remove 100%, it might take 1 day to remove 100% because the rate is really high. You could see the rate is going smaller, and the number of days that it might treat at a higher fraction removal, it might take up to 20 days. So always we need to have a higher K values. This means that the bacteria is very active and we have full degradation or we have full chemical oxidation. So we need to have a higher K value, and of course the time would be less to remove all the organics, or if we have like a higher K value for oxidation or higher K value for degradation. Thank you very much.